Hey everyone, welcome to this explainer. Look, if you're stressing over your upcoming microbiology exam, I just want you to take a deep breath. We're going to get through this. Today, we're building the ultimate simplified study guide to completely demystify bacterial cell walls. We're going to break down this microscopic world into super clear, visual concepts so you can walk into your test with absolute confidence. So, here's a massive question for you. Why is it that some bacteria can just shrug off our most powerful antibiotics, while others get destroyed almost instantly? Well, the answer actually lies in a surprisingly simple dye test discovered way back in 1884. It's a test that literally splits the entire bacterial world right down the middle, and honestly, understanding it is absolutely crucial for mastering microbiology. Okay, here's our game plan for today. We'll start with the Gram-Stain secret, then look at gram-positive, thick and purple, followed by gram-negative, thin and pink. After that, we'll dive into clinical impact and toxins, and wrap it all up with the ultimate exam summary. All right, let's dive right into section 1, the Gram-Stain secret. Developed by Hans Christian Gram back in 1884, this famous staining procedure is basically 4 rapid-fire steps. First up, we apply a primary stain called crystal violet. Then we add Gram's iodine. This acts as a mordant to really trap that dye in. Third is an alcohol wash, which is our decolorization step. And finally, step 4, we hit it with a counter stain called safranin, which is a red or pink color. Now you really want to pay attention to step 3 here. That alcohol wash, that is the make or break moment where our 2 bacterial types completely diverge. Now what's really interesting about this is the actual color change happening under the microscope. See, both types of bacteria start out soaking up that deep purple crystal violet dye. But right after that alcohol wash step, boom, they split into 2 totally distinct camps. One group holds tightly onto the purple, while the other completely loses it and ends up turning pink when that safranin is added. So why does this happen? Well, it's all about their physical armor. Which brings us to section 2, gram-positive, thick and purple. Just looking at the baseline structural difference between these two, it's incredibly clear. Notice the sheer thickness of that green layer on the gram-positive cell, especially when you compare it to the tiny, flimsy layer on the gram-negative one. So that green layer, that is made of peptidoglycan. Basically, it's a polymer made up of sugars and amino acids that gives the cell its rigidity and shape. And in gram-positive bacteria, this peptidoglycan sheath is massive. We're talking about a thick, homogeneous layer measuring anywhere from 20 to 80 nanometers thick. It's literally their defining feature. Okay, grab your notebooks, because here is your first major mnemonic anchor for the exam. I want you to think of gram-positive walls like a really thick, absorbent sponge. When that crystal violet dye is applied, it gets completely trapped deep inside that thick peptidoglycan sponge. So even when the harsh alcohol wash hits it, the dye isn't going anywhere. Just remember the 4 Ps, okay? P stands for positive, which equals purple, which equals a thick peptidoglycan layer. Easy, right? Moving on to section 3, gram-negative, thin and pink. All right, so we know the gram-positive bugs have that thick sponge, but for gram-negative bacteria, things are a little different. Imagine a really thin sponge hidden inside a tightly sealed protective plastic bag. That plastic bag is an outer lipid membrane, and it sits right on top of a super thin, like 2 to 3 nanometer layer of peptidoglycan. So the absolutely crucial point here is what happens during that alcohol wash step. You know how alcohol is great at dissolving lipids, right? Well, the alcohol literally dissolves that outer lipid membrane. It melts away our imaginary plastic bag. And without that outer shield, the thin, flimsy peptidoglycan layer underneath just can't hold on to the crystal violet dye. All that purple color just leaks right out. And because all that purple leaked out, the gram-negative cell becomes entirely colorless. It's totally naked. So when we apply that final red safranin counterstain, the cell soaks it up like a dry paper towel. And that is exactly why gram-negative bacteria have their signature pink or red look when you peek through the microscope. Let's pivot a bit for section 4, clinical impact and toxins. Now, I highly recommend you take a mental screenshot of this matrix right now, because I guarantee it's going to show up on your test. Notice the really strict division here when it comes to toxin production. Gram-positive bacteria, the purple ones, produce exotoxins. Gram-negative bacteria, the pink ones, produce endotoxins. But let's actually break down what that means for a patient in the real world. So exotoxins are proteins that are actively secreted by living gram-positive bacteria. They can be highly toxic and honestly even fatal in small doses. Think of stuff like tetanus or botulism. But because they're secreted proteins, our bodies can often make neutralizing antibodies, or scientists can create vaccines called toxoids to fight them. Endotoxins, on the other hand, are a totally different beast. They aren't actively secreted. They're literally a built-in physical part of the gram-negative lipopolysaccharide outer membrane, meaning they're only released into the body when the gram-negative bacteria actually die and their cell walls break apart. And this brilliantly illustrates exactly why gram-negative bacteria are considered such a massive global public health threat today. That tricky outer lipid membrane, it acts as this incredible, heavy-duty shield. It makes them highly impenetrable to a lot of our standard, life-saving antibiotics, which means infections caused by gram-negative bugs can be notoriously difficult to treat in a clinical setting.
All right, let's wrap this up with Section 5, the ultimate exam summary.
Okay, here are the high-yield bullet points you absolutely need to know. Gram-positive? That means a thick peptidoglycan layer that stains purple. Gram-negative? That's a thin peptidoglycan layer hiding right under an outer lipid membrane, and it stains pink. Why? Because that outer membrane dissolves in the alcohol wash, making it lose that initial purple dye. On the clinical side, just remember, gram-positive releases exotoxins, while gram-negative releases endotoxins. And finally, it's the outer membrane of those gram-negative bacteria that causes their dangerously high antibiotic resistance. Seriously, if you just memorize this list, you are going to absolutely ace this section of your exam. To finish up, I want to leave you all with a bit of a provocative thought. As global antibiotic resistance continues to grow at this alarming rate, will that tiny microscopic gram-negative outer membrane eventually become the ultimate villain in modern medicine? It's something researchers are out there battling every single day. Anyway, thank you so much for hanging out and learning with this explainer. Good luck on your exams, and as always, stay curious.